This is Michael Malak, October 17, 2025. Today I'm going to talk about model quantization, which is shrinking models, LLMs, down so they can fit on consumer hardware. I have three systems at home on which I can run AI models. This is my newest acquisition from early in 2025. It uses the AMD Strix Halo processor, which has an integrated GPU, and the RAM, which is 128 gigabytes, can be partitioned between GPU RAM and CPU RAM. So I have it partitioned as 96 gigabytes VRAM or GPU RAM and 32 gigabytes CPU RAM. I also have an older system that I built around the 4090. Of course, that only has 24 gigabytes of VRAM. And then my employer issued me a MacBook, which of course has unified memory, and as long as you have available RAM, you can run AI models pretty quick. So the processor, again, on that small computer up there, it's a kind of the size of a small, thick book. It's a single chip, but it has CPU and GPU on one chip. Each CCD there has 8 cores or 16 threads, so it has a total of 32 CPU threads, and then it has the GPU on another die right next to it in the same physical package. And I'm sure you've seen what a 4090 looks like before. All right, so let's do some demos. So this is on that 4090 system that we're doing first. And because that has limited memory, I wanted to compare apples to apples between all these systems. I'm just going to use Qwen3 32B, which is 32 billions, quantized down to 4 bits, so 2 weights per byte. So that's comes out to 16 gigabytes of VRAM necessary to hold the weights, plus you add another 20% to handle the KV cache. So, probably about 20 gigabytes out of the 24 are being consumed. And we're just going to pass in this prompt for benchmarking purposes, name the planets. Right now it's loading the model. And it outputs tokens at a pretty good clip. I'm not going to go through the whole thing, but we can get the pace, which is 40.43 tokens per second. All right, let's go to that small computer now. And we'll run on the GPU portion of that small computer first. So not quite as fast, but it's tolerable. And that was 10.64 tokens per second, or about 1/4 the speed of the 4090. Now we'll run it on the CPU. Again, it has 32 threads, so kind of top of the end for consumer CPUs, and it's quite slow. By the way, this Qwen3 is what's known as a thinking model. So between the think and the /think tokens is thinking, and depending on your UI, you can choose to display that thinking session or not. But after the /think, it produces its real answer. And so that was 4.44 tokens per second, or a little less than half the speed. Now, besides just the command line stuff, we can do we can access it from the browser using a Docker image called OpenWebUI. Okay, so we can open up a browser. Now we have a web UI. This, by the way, is going to a different model. So this is going to Llama, which is not a thinking model, so it can launch right into the answer directly. All right. So again, the integrated GPU is maybe 2.5 times as fast as the CPU alone. And then I had a 4090, so current state of the art for consumer GPU is 5090, and which is a little bit faster than the 4090. So that'll be about 5 times as fast as that integrated GPU on the smaller computer. So if you want to get started on local, the best resource is on Reddit, the subreddit named Local Llama. I know there's a lot of noise on some of the Reddit subreddits, but this, in my opinion, is one of the top two or so on all topics on Reddit, and it has an endorsement here from no less than Andrej Karpathy. He was doing AI at Tesla and then OpenAI. And he says it's his go-to source for information. So it's a very high level of signal to noise. You can just keep up with all the latest. Hiking Face is like the GitHub of models. And these are the names of 3 accounts of people who are very aggressive at quickly turning out quantized versions of models as soon as they're released. So let's talk about bit depth. So the old FP64, that's the double floating point, that's used for high performance computing simulations such as weather or nuclear explosions. FP32 was the standard for machine learning up until about 2017, but then that's when hardware started coming out that did FP16 natively, or BF16, which is Google's format for their TPU, tensor processing unit. These days, last year or two, GPUs have been able to do FP8 natively, and into 8 would be the largest quantization target that we have. Skip 7, nobody uses 7, 6543, and you can start to see the asymmetry here in the numbers. There's one extra negative number, like -4 to +3, then there are positive numbers. So that's why when you get down to int2, you pretty much have to change your 0 point so you don't actually have a 0, but the weights are centered around 0. Or if you don't want to do that, there's ternary, which only takes 3 values. And so with data compression, that averages out to 1.58 bits per weight. And there is even int1. I think Microsoft is the one chasing this the most aggressively. So how many bits do you really need? Well, as you can see from this chart, the knee in the curve is 5 bits, and beyond that, it's diminishing returns and accuracy. A lot of people choose int4. It's very convenient, 2 weights per byte. So let's go over some terminology. So I kind of mentioned this asymmetric versus symmetric before. If we really did 2 bits asymmetric, we would have this strange situation of -2101. But once you get up to 8 bits, or not even quite that many, you can do this straight through map 0 to 0, and usually you would go from -127 to +127, just throw away that -128 code. Another thing you can do is sort of this log scaling, because the values close to 0 are more important, influence the final result more than accuracy on the larger values. So this is kind of like exponentiating the value, the straight line value. And again, the weights closer to 0 are more important. Now, I guess kind of what we've been talking about so far is global. Kind of the naive approach is you have the same number of bits per weight everywhere, but you don't have to do that. You can vary the number of bits depending on what part of the model you're talking about, which layer, which block, which channel, etc. And not just the number of bits, but also the scale and the linearity. And finally, there are 2 major types where we can target weights or weights and activations. So in weights, you're doing all your math still in FP16. Your 2-bit weights really just serve as data compression. You take your 2-bit weights and decode them into FP16 and do all your math in FP16. Whereas with weights and activations, you do your math in the integer domain. Everything's in 2 here in this example, except when we're computing our activations, we're accumulating values in our dot product, so we don't want that to overflow, so we just make that in 32 before we quantize it back down to int2. And that's what this hat means. So I use the hat symbol to mean the quantized version. So this is a good rule of thumb on how to calculate how much VRAM you need. This is actually for my current favorite model, which is Qwen 3 235 billion. What we saw before was just 32 billion, and that was so that it could fit onto the 4090, the limited VRAM there, 24 gigabytes. But with the 96 gigabytes on the Strix Halo, I am able to run this because it only comes out to 76 gigabytes total. And again, that's 235 billion weights, and going 2 bits per weight. You can see immediately that's like 65, and then you have to add, a fudge factor for your intermediate values in cache. And again, this is just a very rough estimate because there are all these things that really affect what the real needed memory is. So context size, so the number of tokens that you can enter and output. If you specify a larger context size, like 16,000 tokens instead of 8,000 tokens, that's going to require a larger cache. Mixture of experts can really save time and money. So, like, people were disappointed with the accuracy on Llama 4. It really wasn't much better than Llama 3.3. But Llama 4 was way faster because it was mixture of experts, having 8 smaller models and a router that directs which model to use. It means you're running only 1/8 the weights at a time, so you don't need as much cache, and it runs quite a bit faster. And then the dynamic quantization widths that I was just talking about. So why quantize? Again, it's so that you can run on consumer hardware. So Strix Halo, again, that's my new favorite little system. NVIDIA, of course, owns dedicated GPUs, so my 4090 is up here. And you may have seen this past week that brand new, the DGX Spark was just released. That is a small self-contained computer like my GMK Tech that I've been talking about, or I guess another example along those lines in terms of form factor would be a Mac Mini, so that would be down here. Intel really hasn't been doing very well in terms of supporting AI. Like if you just use a regular CPU, you run into the problem that some cores are E cores, efficiency cores, and some cores are P cores, performance cores. And the E cores, the efficiency cores, don't have the full AVX instructions, which are used for the matrix multiplication. But probably in 2026, they'll have P core only CPUs once again, finally. Their integrated GPU is kind of weak, and they're still reestablishing the direction on dedicated GPUs. A lot of people on the local llama like to use this EPIC processor. So this is an expensive processor. It's like $10,000 or $20,000, and you can have 1 or 2 of them if you have 2 sockets. But it has 256 threads, and more importantly, there's no need for VRAM. It's just RAM, and of course you can stick 1-2 terabytes of RAM on a motherboard and have 512 threads hitting it if you have 2 sockets populated. And finally, one of the reasons we want smaller models is so we can run them on the edge, as they say, which means just running it on your cell phone. So the iPhone 17 can come with 12 gigabytes of RAM totals. Again, that's kind of like unified memory on the Mac. So you could devote 8 gigabytes of that to, say, Llama 8 billion parameters. So drilling down into NVIDIA, so ignore these two new ones for the moment, and even ignore this bootleg one. You can see NVIDIA was intentionally creating this chasm between consumer products like at $3,000 versus their enterprise products at $30,000. Uh, and they did that so that enterprise customers wouldn't, cheap out and get a consumer version, and they ensured that they didn't by keeping the VRAM intentionally small on these consumer versions, until small companies in China said, okay, we're just going to take these 5090s off the shelf and add more memory, and you can get these on eBay. But finally, in the past few months, NVIDIA has started to fill in this chasm, uh, what I would call the prosumer market. So the RTX Pro's 6000, it's $9,000, which is pricey for a consumer, but not totally out of reach. And of course, then the DGX Spark that just came out this past week, and at 120 gigabytes, and I guess more importantly, you can gang two of these together and you can get 256 gigabytes. When you go to download those models off of Hugging Face, you'll probably be downloading GGUF models. Those are the quantized models. Um, the PyTorch format can handle both quantized and unquantized formats, but I think Llama CPP, which is what I used most of the time and what I did the demos with, prefers GGUF. And then finally, there's the Safe Tensors format, which is very annoying because it has all these extra little files that have to come along with it. So when you go to Hugging Face and you go to download some of these models, you can see there are quite a number of options. To help decode what these file names mean, obviously the llama and the 3.3, that's the model name and version. The next number is the number of weights, and then the word after that is the fine tuning. So there's instruct, which is for basic chat, or what we've come to become used to in terms of LLMs is the chat mode. That's what instruct is. There's also base. So base, now if you remember what the point of a language model is it predicts the next word. So base models, if you type in we the people, it's just going to continue on and say we the people in order to form a more perfect union, etc. But it was, ChatGPT 3.5, when that came out, that was an instruct fine tuning, fine tune just for chat. If you type "we the people" into ChatGPT, it's going to say, "Oh, these are the first few words of the Declaration of Independence, and here's the rest of it." So it's trained, fine tuned for carrying on a dialogue. And besides instruct and base, there are other fine tunings like for coding. Then you have this prefix IQ versus Q versus UDIQ. Those are different classes of algorithms in terms of dynamic number of bits and scales and so forth. Uh, well, the thing after the Q is the number of bits, or the prefix is the number of bits. So 2 bits, 3 bits, 4 bits. And then you get into the different classes of algorithms. So 0 is the base straightforward, same number of bits per weight everywhere. 1 is a slightly modified version of that. So 0 and 1 are the old formats. K is what is the current format. And within K, then you have these t-shirt sizes about, how often the weights will expand beyond the base. So, you know, a Q4K medium is going to have more 5 and 6-bit weights, for example, than a small, even though the base number of bits per weight is 4. And then if you have a mixture of experts model like Llama 4, as I mentioned, it actually has 2 numbers here instead of 1. It has the 17B for the number of weights per expert, 17 billion weights per expert, and then 16 experts. So the total number of weights would actually be 17 times 16. So you would need to take that into account when you're doing your rough calculation for VRAM requirements. Uh, User interfaces. So you've seen the CLI and you've seen the web UI, and then underneath the hood of the web UI, I was running um, llama.cpp in REST mode. So I have some standalone programs that will hit the REST server, and it's the most probably the most common interface. So the way we can get quantized models break out into two major categories: post-training and pre-training, or during training. Pre-training is really during training. Post-training is the most straightforward. You have your regularly trained floating point model, and you want to make a quantized version of that. So the naive way would be, you just take your floating point values, clip and round them down to integers. Problem is that creates cumulative errors. As you do your multiplies and accumulates for your dot products and matrix multiplications, you just get cumulative errors. So we don't want to do that. We want to be a little bit smarter than that. And so the very first algorithm that was a little bit smarter was called optimal brain quantization. It actually serves as the foundation for the current algorithm, which is GPTQ. And I'll mention what the additions are that GPTQ adds. Basically, they're just embellishments to this core algorithm here. And they framed the problem of wanting to minimize the difference between using the floating point weights and the quantized weights. Again, the hat means quantized, so these are the quantized weights. And what that difference means in real life. So we're actually taking our x and multiplying it into the w, and x into w hat. And that's what we want to minimize to come up with our optimal weights. I'm using asterisk to mean optimal. And this x here is actually not just a single vector. It's what's called calibration samples, which could just be your testing set that you held out. And it's multiple samples from that test set, and they're just kind of stacked up. And so this is actually, it can, or actually really is, batch processing. So X is a matrix. Uh, we have M number of calibration samples, uh, and then D activations for the layer. If this is the very first layer, then activations is really just our raw input. So the basic algorithm is to you process the weights in order. You take a row of weights and you just process them from left to right. Uh, and to do that, uh, we calculate this thing called the Hessian, 2x times x transform. And that Hessian is actually an approximation. The true Hessian is involves second derivatives. This is we're using an approximation. Once you have the Hessian, then we compute this delta f based on these values from the Hessian, and taking W, our current weight, minus its quantized version, and then we take that delta F and we add it into the remaining floating point weights within the weight. So the F stands for the set of weights that are not yet quantized, or still the full precision weights. So as we march through the row of weights, that this WF gets shorter and shorter as we distribute the error amongst the other weights. Now, the reason we use the Hessian is because it's very good at detecting correlations. So the general idea here is that if we have an error, if this w minus w hat is large, we want to distribute that to columns that are similar or correlated to the column that the weight is from. So sometimes we like to think all our features are totally independent, but of course that's not true. For example, if you have weather data, you might have thermometer temperature and heat index. Uh, they're not going to be exactly the same, but if you have a large error on your thermometer temperature, you want to distribute that to the heat index so that it can compensate. And this is really the Gauss-Newton approximation of the Hessian. So why the Hessian? I've kind of mentioned why, but this is a little deeper dive into the intuition. So this is the X that we had before. We have M calibration samples, D activations, but we can also write it like this. It's the same exact matrix. We're just considering it like, okay, for activation 1, we have all these samples. For activation 2, we have all these samples. And then you take the transform of that, and those become columns. And when you multiply that, you see that it's actually, we're taking the dot product or inner product of each set of samples for a particular activation with another set of samples for a different activation. So activation 1 with itself, activation 1 with activation 2, 1 with 3, 1 with 4, etc. And so this actually shows correlations. Um, so H represents similarities between activations, but remember for the formula for this delta F actually involves the inverse of the Hessian. Um, and so when we take the inverse, then that gives us the dependencies that we want between activations. So that was one weight at a time in order, but uh, you know, much more commonly and effectively, um, we look for low-hanging fruit first. And what I mean by that is uh, we're going to be choosing Q, which is the index of the weight that we're going to optimize. And we choose Q depending on uh, the error for the weights. So if a weight happens to be close already to a quantized value, then this is going to be small, and we're going to want to quantize that first. In other words, if a weight is already close to being quantized, just quantize it, get it over with, and we can focus our attention on the weights with larger error and distribute those. And so after we've decided what our Q star is, then we're going to be picking out different values out of the Hessian. So in the previous slides, this was just 0, 0 and colon 0, which means the first column. But now we're going to be picking out particular values. So let's actually go through the math derivation of why we're using the Hessian. So if we have our weights and our input values, then y represents our output values, and what we're going to end up doing down here is calculating this delta y um, uh, between the quantized version and the non-quantized version. So EQ is non-quantized minus quantized. And then in the next couple of slides, we're going to minimize delta y. And if you remember from first semester calculus, the way we find the minimum of a function is we take the derivative and set it equal to 0. So up here we set that up, and then we take the derivative, set it equal to 0, and solve, and we get this. What we really want is we want delta f by itself, so we're going to divide both sides by xf transform, which is actually, since these are matrices, taking the inverse. And this is basically our answer. Once we represent our Hessian, we know that's 2xx transform. So we just substitute that in and we get our result. That's why we're using this formula. All right, so the embellishments that GPTQ adds are, computing the inverse of the Hessian. Each iteration can be slow. There are ways to do that in an incremental fashion, so you don't have to recompute it from scratch each time. And then, uh, this inverse of the Hessian changes um, each row, uh, but if you use the same order of weights each time, Um, you don't have to do that, and it turns out that the order, if you keep the order the same from one row to the next, that works out pretty well because it's the columns basically have the same properties from row to row. And then some of these models can have thousands of columns, so to keep things sane, they'll usually batch those down to 256 columns at a time and distribute the error only within that set of 256 within that batch. There's another way to make the H inverse even faster, and that's the Cholesky reformulation, which I'm not going to get into. And then finally, this little trick of adding lambda times the identity matrix, small value for lambda, just to make H more stable for calculating the inverse. Now, this is a paper that came out just a couple of weeks ago. It says that GPTQ is really just solving the closest vector problem. Now, it just so happens, and the paper didn't really get into this, but closest vector problem is also the foundation for post-quantum cryptography. I'm sure you've heard that RSA, the foundation of HTTPS, is under threat of being cracked by quantum computers, maybe by the year 2040. So they're already, looking at uh, cryptography algorithms that cannot be cracked, or they think they cannot be cracked by quantum computers. And one of the leading algorithms for that is called the closest vector problem. And that is, if you're at the yellow dot, which of the white dots are closest, these intersection points within a lattice. And, that's easy for this two-dimensional problem. But again, remember, we're talking about vector spaces that are thousands of dimensions. And there it becomes an actually difficult problem. So, uh, this correlation, this isomorphism identified by the paper between GPTQ and CVP allows all the knowledge developed under CVP to be applied to GPTQ and come up with some nice results and shortcuts and so forth. This is another interesting paper that came out less than a month ago. So if you happened to be around in the 1980s, then you saw the bit wars on CD players. When CD players were first introduced, they were only 14 bits, even though the CDs themselves were 16 bits. The following year, 16 bits was the standard. Then we got into these wars where manufacturers started interpolating to recover the analog waveform more accurately, make it less stair-step. So then they had 18 bits and 20 bits, but if you think about linearity, right? So the 20th bit uh, is 1/millionth the voltage of the first bit. That's because 2 to the 20 is about a million, and that's because 2 to the 10th is 1024, and 1024 times 1024 is 1,048,000 something. So if your bit 1 is 1 volt, that means your bit 20 is a millivolt. How do you ensure that your millivolt is exactly 1/millionth of your 1 volt? So that's when they came up with 1-bit CD players. They just interpolate the 16 bits extremely fast. It's kind of like pulse coded modulation. And then, that creates a lot of high frequency noise. So they just filter out that high frequency noise and they end up with a more linear output because 1 bit is always linear to itself. You don't have to worry about something 20 bits away. And that same theory was applied to large language models. Basically, everything is 1 bit. All your weights are 1 bit each, except if you have a weight where you really need that extra accuracy, you split it into multiple 1 bits. And then those all just get added and averaged together, kind of like this sigma delta quantization from 1-bit CD players. Finally, well, this three uh, recent papers. So this is slightly older than a month ago, but this is leveraging the idea of rotating a vector space. Actually, there's another technique called spin quant that we'll get into later. Uh, spin quant is for quantization aware training. The reason that rotating a vector space can help is it can push more of the weights away from zero so that they don't just get rounded down to zero. And we can do this rotation because we keep everything the same by not only rotating the weight matrix, but we also rotate our input vectors so that um, the rotations cancel out. And the butterfly quant technique uses that rotation, and it does it two axes at a time, and it takes this inspiration from the fast Fourier transform. And this is called the butterfly pattern, and this diagram is actually straight out of the fast Fourier transform, but it's the same kind of pattern where you do two at a time and then two at a time from adjacent siblings, if you will, and then you end up with passing through all possible combinations. And then uh, each rotation of two dimensions, this is what the rotation matrix looks like. If you've done any kind of computer graphics, this is the standard 2D rotation, cosine, sine, minus sine, cosine, and then when you apply that to a higher dimensional space, you just have the identity matrix in the other positions. So doing this ends up, even though you're doing a lot of individual rotations, it ends up being a lot faster than doing one big dense rotation. And that's completely analogous to the Fourier transform. Fourier transform, again, is where you take something like an audio signal and create a spectrum out of it. So the straightforward algorithm, discrete algorithm, has n squared complexity. The FFT, due to the butterfly pattern, has n log n, and it's the same thing in the rotation. We have many sparse rotations that are easy to compute because almost all the coordinates are 0 and 1, and we end up with n log n complexity, as opposed to if we had one big massive rotation matrix where, well, it's the same size physically, it's just you have values here other than 0 and 1, and that would be n squared. So how do we know how much to rotate by? Well, that's learned. So after, again, this is a post-quantization training method. So after our model has been trained and quantized, we freeze those weights uh, and then run our training data through it again. And when we back propagate, we don't adjust our weights, we adjust our rotation angles. And these angles are not just simple 30 degrees. These are multi-dimensional angles. Okay, so now we get into quantizing during training. And spoiler alert, this actually ends up with results that are more accurate. So what we've been talking about is PTQ over here on the right. But what we're going to be talking about now is quantizing during training. And it would be more accurate to say retraining, right? Instead of randomly initializing your weights, you'll probably just start off with your fully trained model, floating point model, and retrain by running your training data through quantizing the weights as you go through. And so this is the standard regular training. You run your training example through your model. This is called the forward pass. Compare it to the label value, get a delta, and run that loss back propagation through. The difference here is that when we do our forward pass, instead of using the full precision weights, we quantize them on the fly and used quantized versions of the weights. Now, it's just common practice in this QAT to just keep everything stored as full precision and quantize on the fly. And so that's called fake quants in the literature. And then on the back propagation, that's basically the same as before. We just have to be a little careful about our clip range. Uh, so this is showing that QAT is closer to the original floating point accuracy than PTQ. And besides learning the rotations, you can also learn the scales and 0 points. Or you can do this rotation. And uh, you're doing your forward pass with fake quants again. And in this case, you're applying your loss to both the weights and the rotation angles. All right, so let's look at some code. So these are our formulas. I'm just using sklearn here. So, you know, if we wanted to cheat, we would just load up PyTorch or TensorFlow, and that has quantization uh, algorithms built in. But here we're going to be implementing that very first slide, just processing weights in order. So we're always going to be picking off the 0, 0 and :0 off of the Hessian inverse. So this is just set up, and then we need a model to quantize. So we're just going to train a model on the fly here. So this is the good old iris data set, and it's going to have 2 layers. The arrows kind of represent the layers. So 2 inputs, sepal length and width, 3 outputs, which of 3 types of flowers, and then a hidden layer of 16 weights. So hidden equals 16, and this is just standard ReLU softmax stuff. Um, here's our back propagation. And you can see our accuracy here from previous run. Okay, so now we get into our actual algorithm. So this is a helper function. This is just rounding a floating point value to its closest quantized version. We're going to be doing 3 bits, and the way this is written, we do just like -3 to 3, so we're throwing away the -4 code. So we have, that gives us 7 possible values: -3, -2, -1, 0, 1, 2, and 3. And this is applying a scale, so we're going to have uh, the same scale factor for every weight in a layer, but from one layer to the next, we'll have different scale factors. So that's why this is called layer global scale. If you pass in a weight, um, it'll compute a scale. And then quantized row and order is the heart of our implementation here. And that just gets called many times in a row from quantized layer in order. So let's look at quantized row in order. So D and M are dimensions from X. Uh, we take a working copy of the row, and then WQ out, that's going to be our return value down here. Uh, this F is our set of weights. Actually, we're just going to be processing in order, so we're not going to be really using the F in this example. but then for each, we're processing one row, so for each element in our row, we compute our Hessian. Again, this is not optimized. We're not doing any kind of incremental calculation to compute our Hessian. We're computing it from scratch each time for each weight. So again, that's XF times XF transform. And then we do rely on just the NumPy inverse to invert that matrix. And so we're doing things in order, so we just take F0. So our W hat, remember we use hat to mean quantized. Our quantized version is the working copy run through our quantization function. Our E is the working value minus the quantized version. And finally, this is our key formula here, where we're computing our delta vector that we're going to be adding to the weights. And this is where we use our two Hessian values. And then we store our quantized version into our working vector. And then finally, we take our much sought after delta vector and add it into the rest of our unquantized weights. Our full precision weights get tweaked by this delta. And we update our return value and go on to the next iteration. We return that, and this is where we call that quantized row in order in a loop for each row in a single layer matrix. And we execute that, and these are what our weight matrices look like. You can see that in our first layer, everything is like a multiple of 0.48. Here you get this 1.44, that would be 3 times 0.48. This is the way we store the quantized weights in this algorithm. They're in the represented as full precision. What's not shown here is reducing that actually to our 3 bits. But the second layer has weights that are multiples of 0.46 instead of multiples of 0.48. And again, that's because we've chosen a different scale factor here for these weights to better accommodate that range. We have a different scale for each layer in this example. And now we evaluate our accuracy. And you can see that the 3-bit actually has the same accuracy as the 32-bit floating points, but the space required, the RAM required for those weights is 1/10 as much. It's only 37 bytes, but obviously this is more applicable to large language models with billions of weights. All right. So just to wrap up, so quantization is actually just one of a dozen or dozens of techniques to make models smaller. So I'm just going to list off some of these others. I'm not going to go into any of them. Distillation is where you have a large teacher model and you train a small student model based on inputs and outputs out of that teacher model. Pruning, that's like dropout, but you can prune even larger amounts, like entire layers sometimes. Supervised fine tuning. So sometimes instead of relying on a large model that has a lot of general knowledge, you can take a small model and fine tune it with exactly the data you need for a particular use case and just rely on that. And of course, you've probably heard of RAG. So again, instead of relying on the general knowledge contained within a large language model, you can have a smaller model and feed it retrieved documents or pieces of information insert that into the query so that the small model can have access to that extended knowledge. And finally, the same low rank algorithm used in LoRa, if you've heard of the LoRa algorithm, that same sort of concept can be applied to these large weight matrices where you can approximate a large weight matrix with a small matrix. I encourage you to send me an invite to LinkedIn if you found this interesting. And that is it.